Choose Ivan Marusic, who will give the first invited talk on accurately measuring and modeling near-wall turbulence. And you all probably know Ivan. He has had a career both in the States and now in Melbourne, where he's managing maybe the biggest wind tunnel for turbulent mountain research. Okay, so please.
Thank you, Henry. Thank you for the invitation. I was supposed to be here. I was one of those affected by the volcano, and so Henry asked me for a talk. I had prepared a talk. I was supposed to be here last Friday, and Henry asked me to prepare a talk for a very general audience, and I did that. But then I realized that here it isn't really going to be, it's very people who are well informed of the topic. However, so I sent him two titles, that was one, and I have to acknowledge my co-workers, Ramon Mathis, who was here as part of the program, Nick Hutchins, Jason Monty, who are my colleagues at Melbourne, Henry Ng, who's my PhD student, and Lex Smith for some of the work that we've collaborated on. This is another title that I sent in, and that's more reflective of what this talk is going to be. It's a talk on experiments modulated by this Icelandic volcano, and so this is going to be disjointed. Henrik asked me to include some historical aspects, and I was reluctant to leave them out, so I've tried to integrate it, but so bear with me for the first 10 minutes or so. So a little bit of, so the outline, I'll cover a little bit of history and give some very incomplete highlights of what I see some of the main early work in wall-bound flows, mainly before the Second World War. And then I'll talk, I'll change gears a couple of times, talking a little bit about hot-wire anemometry and the challenges that we face. It seems an annoying problem. We've been working on this for a long time, but there are still many challenges, particularly as we try to push the very high Reynolds numbers. And then issues remain as to how to do that, how to model for those effects, correct for them if needed, and work towards better understanding this near wall region. So just first some details about very early pioneers in wall confined flows, so not necessarily turbulence. And really one of the first people is Henry Darcy, who studied flows in confined pipes and channels. Here are some of his technicians making measurements with a pitot tube in an open channel. And really this is part of the hydraulics literature early on. And then a very famous person who studied flow in a pipe. There he is with his pipe, taken from his paper. And if you actually go to Manchester, there's the actual original pipe. You can see it on display. And the point is, in his 1883 paper, Reynolds actually quantified this number in this form, and it wasn't actually to his 1895 paper that he wrote things in the conventional way that we're used to seeing them. And it was Sommerfeld who picked up the term, who I think first coined the phrase Reynolds number in 1908, and then later Prandtl himself in his 1914 refers to the drag coefficient as being a function of the Reynolds number. So that's sort of stuck with us ever since. It's interesting, I said bear with me, but I found some of this interesting. There's a nice annual review paper by Jackson and Lauder. This is actually a section of George Stokes's review of Reynolds' paper. It's in the Royal Society archives. And he makes a point saying, of course, he recommends publication, but he points out that Reynolds shows for the first time the distinction between regular and eddying motion depends on the relation between dimensions of time and velocity. And he also makes the point that it's a relation which is pointed out by the known equations of motion of viscous fluid. So I think that's an interesting point. Something I think, at least in my experience as an undergraduate, I don't think that's very well taught. We always talk about a ratio of inertial to viscous forces. But what Stokes is saying essentially, of course, if you take the Navier-Stokes equations and you non-dimensionalize them, you end up, the Reynolds number comes out explicitly within the equations of motion. So it's implicit to the equations. And Reynolds studies, of course, looked at the transition, quantifying a critical Reynolds number at which we see a transition. But for us, perhaps more important, those looking at fully developed turbulence, Reynolds number is a ratio of the scales, the length scales, velocity scales, or time scales. And so at high Reynolds number, obviously, we have a large range. So here's a nice example of a flow with a large range of scales. This is continuing this volcano thing. So you can see these plumes, which are at least as large as the scale of the mountain. And then we get down to very, very fine details, and you have a continuous distribution of scales. So that's just a brief introduction. In terms of wall-bound turbulent flows, really the work starts, of course, with Prandtl. And it was in his paper, which he presented at the Third International Mathematical Congress at Heidelberg, sort of an obscure place. The paper was all about addressing D'Alembert's paradox. And basically, he developed boundary layer theory to address that. And really, it was rather an obscure place to publish, and it wasn't really recognized by the rest of the community for a while. Dryden reviews the first 50 years, and he noticed that in the first 5 years, there were only 5 workers or 5 papers really on boundary layer theory, and all from Göttingen, involving Prandtl and his students and a colleague as well. Von Karman was there as well at Göttingen at the same time. However, his involvement with wall turbulence really came later in the pursuing years. By the end of the second decade, so 20 years after the paper was published, there are still only 3 groups working in this problem. Again, Göttingen doing the bulk of the work, von Karman at Aachen and at Delft. And Burgers was the person leading that charge. And he reported, in 1924, the first real observations of the velocity profile on the boundary layer. Up till then, Prandtl had done lots of work visualizing boundary, looking at suction development, more global properties. The challenge was it was very difficult to measure within the boundary layer because it was so thin. And so it needed development of new probes. And really, it was not until the development of hot wires, and really the key work was done at the National Bureau of Standards, at that time headed by Dryden, and he presented these measurements in 1934 for the first time. After that, there was a considerable flurry of activity, and most of the main work coming again at the National Bureau of Standards under Schubauer, and then, of course, Townsend at Cambridge and Ludwig and Hillman. There's lots of seminal work on early characterization of turbulence and boundary layers. Just some more photos. So this is the actual, I don't know if some of you have seen the famous movies by Prandtl, but actually Maury Garib showed it. He analysed the surface flow patterns using PIV and was able to, that was quite interesting at the last APS. But this is the rig. And again, a series of very influential characters at Göttingen, von Karman, who then went on to Aachen and then Caltech. But also, I need to mention Nicorazzi, who really did an amazing set of experiments by anyone's standard. This is from his papers. The reproduction is not very good. But he was able to map out the friction factor as a function of Reynolds number over an enormous range with varying roughness. That's really an unprecedented experimental data set. Of also particular note is the work at the National Bureau of Standards. Dryden then went on to become a senior administrator. I think he was a deputy administrator at NASA. And this is a very famous result. Not only did they develop the hot wires, but also they saw that they needed to go to very high quality wind tunnels. So they were the first to demonstrate Schubauer and Stromstad in fact, they published this in 1943 in an internal report, but it was not released 4 years later. They demonstrated for the first time that you actually can have this linear instability phenomenon where you have atomic shifting by breaking down, but you needed to have a very well-controlled environment to demonstrate that in the laboratory. So that's sort of a little bit about some of the early history. This is also a little bit historical in terms of the development of hot wire anemometry. It's interesting that a technique which is, sorry, anemometry spelled incorrectly, but it really hasn't really undergone development for a long time. One of the people who did a lot of work on this is Tony Perry at Melbourne. The biggest change in hot wire anemometry came with the advent of integrated circuits. Then all of the constant current anemometer were basically thrown out, and people started using constant temperature anemometers because we could have high bandwidth op amps. Constant current anemometers are basically now used simply for temperature measurement. The problem with them, you have to compensate them. A natural wire on its own will typically have a frequency response of about 1 to 2,000 hertz. That's what the heat transfer gives you. Then you have to put into a circuit, play games with it to get higher. And in theory, a CPA can take you up to hundreds of kilohertz, but it's actually quite a challenge. And really, since those days that those first anemometers were developed by DISA, they haven't really done any work extending the capability. So we're still, and one of the people who really studied it as a science was Tony Perry. He has a series of papers in JFM starting in the late 60s, where he went through and analysed the circuitry, the aeroelastic behaviour of the wires themselves, and tried to put a firm scientific basis to the technique. And also at Melbourne, he developed a series of flying hot wires. So these are quite unique. It was the original flying hot wire was built by Brian Cantwell and Don Coles, but this was a rotating arm, a swinging arm, so you measure them essentially at a point. Here you traverse over long stringwise distances, so these are carriages which ride on an air-bearing sled. And then basically the whole idea, of course, is that if you traverse the wire at significantly high speed, you reduce the effective turbulence intensity that the wire sees, because if the instantaneous vectors to the wire are too large, you can get erroneous measurements in high turbulence intensities, so in strong adverse pressure gradients, or in reverse flows. Of course, the hot wire makes no sense because it doesn't know anything about direction. So this is the original hot wire built by Johnny Watmar. This is a 4-meter length wind tunnel, so you can see it flying backwards and forwards. This is inside the wind tunnel. So there's the wire. And in this case, they were looking at wakes. And of course, you have a problem that you're going to hit the top line. So they came up with this ingenious device to prevent that. My PhD was actually using this, but in a favorable adverse pressure gradient. So there's always challenges. I never go back to the beginnings. Lots of challenges. So that sort of concludes my historical aspect, and now I'll talk more about the specifics of measurements in boundary layers. So you're all familiar with the flow visualization of a turbulent boundary layer. We put a probe in at a particular wall normal distance, and we traverse the wall normal distance, and we record statistics. So it's a very simple thing. However, there are challenges, as I said. This is actually quite a high Reynolds number of a Kalman number, or Reynolds number, friction Reynolds number of about 14,000. And you can see a very nice looking mean velocity profile, by just staring at that, that looks pretty logarithmic to me. But you see that when you get down close to the wall, remember this is a logarithmic scale, the peak intensity in the turbulence is at nominally a wall normal distance Z plus, I'm using Z as wall normal, of about 15, 12 to 15, that sort of range. And there's been a lot of discussion of late as to what that level is, how does it change. If you do a survey of the existing data, you get something like this. And this is restricted. This is where I've neglected, only considered things with a length on diameter of greater than 200. And there's a lot of literature with less, so I've left those out. And this is what you get. It's just basically looks like a scatter plot. And you know, the classic theory will say that this should be a constant. So all of those should be on a line, a straight line like that. And then there's other theories which said there should be a weak logarithmic dependence. It's very hard to discern anything just by looking at those data. So obviously that's made us go back and look at these things in more detail. The challenge, of course, is it's very difficult to access that part of the boundary layer by Reynolds number. So this is just the back of the envelope calculation. If you want to be at that position where the peak intensity takes place in a boundary layer, or in this case, if you have a pipe about 150 millimeters diameter, sort of a typical size that you see in a laboratory, then you see that if you want to get to higher Reynolds number, this is what I would call high, once you're getting up at 10 to the 5, oil pipelines are around here. You need to get, for this value, you need to get down, the position is 11 microns from the wall. So obviously you need a small probe. Even a single wire itself is going to be very close to the wall in that particular case. And so you do have a real access issue. So here are a collection of more recent data. This is a compilation put together by Fernholz and Finley, now showing across, and this is in the Princeton Superpipe by Jonathan and Beverly and Lex and others. And you see that it's a little bit hard to read, but at the highest Reynolds number, so this is 100,000, it stops here. So you can see that in this particular, you can't get much closer to the wall with a conventional wire. And you're really blind to everything that happens. So we have a fairly good idea what happens in this outer part. Again, this is very close to the wall. You're using this as a single wire. But you're very limited in the access. And then questions remain about what actually happens in this inner region. You can see that here the data show two interesting. One, that things collapse in inner variables, so things that suggests that we should have a constant. But also you have this appearance of this second peak in the outer region. In both, just by glancing at if you scrutinize them a little bit further, it's not so obvious, but just by glancing you would suggest that there is an outer peak emerging at high Reynolds number, which is not there at low Reynolds number. It's something that's been bugging me for a while. I actually think it's real. If I had to guess, I would wager that you do actually get that, but not at these Reynolds numbers still. I think you have to go to, perhaps in this case it is, I'm not sure, but definitely not at 20,000, which where these stop. So the reason I say that, because so at Melbourne, the way we decided to tackle this problem, this really started for me a long time ago when I was a postdoc, is the only way you can really, rather than building extremely small probes, which I'm not good at, you can go the other way and make things extremely big, so slow and big. So we have a large wind tunnel with a very long working section. This is a photograph looking down the working section. So essentially it's just like what you would see on the plane, on the fuselage of a plane. A boundary layer develops over a very long distance. You don't need a very high speed. And we typically have boundary layers of the order of 350 millimeters. So they're quite high. We still have problems getting very close to the wall, but at least you have a fighting chance now with a conventional probe. And so these are some measurements that we took over fairly low Reynolds numbers up to quite a high Reynolds number. We can go higher, but we don't have reliable data yet. Because even using 1.5, 1 micron lines, it's quite a challenge. So, but what we see up to this Reynolds number, we don't really see an outer peak. You see this sort of shoulder, but you see this very small systematic departure, which is sort of, and that essentially goes as a weak logarithmic. I should note that we have significant viscous filtering going on here, 22 viscous wall units. And that number sort of came from the work of Ligrani and Bradshaw. The problem with that study was confined to a Reynolds number of 1,000. And so the question is, are all of those rules of thumb that we've developed for the low Reynolds number, can we use them at high Reynolds number? And this is always a challenge when you enter a new regime. You have to test those things. So I actually think that the peak is considerably higher, perhaps up here, and this is actually an attenuation due to the sort of, and you know, DNS is no different. Gary spoke about these things. You know, what are you comfortable with in your span-wise resolution to see these effects? It is clear, though, that there is a first-order effect once your sensing length is large. And these aren't big wires. This is a conventional 5-micron wire, about 1 millimeter, at this Reynolds number of 14,000. So this is by no means what I'd call very high Reynolds number. But you see this systematic attenuation of the energy. And what's interesting is just the extent at which it manifests itself. It's much further away from the wall than you would guess just by you know, simple arguments. But here, of course, you see this second peak, but it's definitely a manifestation of the spatial resolution in this case. Now, whether that's true of higher Reynolds numbers, I don't think we can say. It's instructive to decompose the sim. So these are those same 3 plots. In this case, I decompose them into large-scale and small-scale contributions. In this case, about 7,000. How did I get this number? Well, that's just by looking at a partition in spectral space. And it's not ordered delta in any case. But you see that the attenuation is dramatic here for the, as you'd expect, for the small-scale motions. And these outer-scale motions, the large-scale motions, are not affected even in this region here. So these are large-scale motions which you can see contribute all the way down to the wall. Okay? So I'll come back to that later. This is a spectrogram showing the same thing. So basically, if I integrate across there, this is I'll get a number. So this is wall normal distance. This is wave number. And you see the appearance of these 2 peaks that I'll mention later again. That this inner peak, which is associated with that large energy at Z plus 15. Also, the same location where you're going to get these predominant streaky near-wall streaks. But also you see this bulge in the energy out basically in the middle of the logarithmic layer, where the log layer is classically believed to exist. If you filter, if you use a bigger Y, you basically get rid of all of that. So all of that disappears. Again, but it's also a case where you're also filtering scales which we wouldn't have thought they go out that far. It's really a long-range effect. So this is also something which has been debated in the literature. Is there a K to the -1 law in the streamwise spectra? So this is pre-multiply that. A K to the -1 would mean a plateau. So you can see here we have, this is as reported by Nichols and ourselves, you have this sort of small region of K to the -1 in the data. This is RE tau of about 14,000. So again, it's not terribly high. But the issue is we can push the Reynolds number up in our tunnel, but we can't trust our hot wires well enough with those. So we're working on that. The issue is drift. And small wires are very drifty, so particularly when you get at below 1 micron, at least with existing technology. And this red line, you know, if you were designing an experiment, you would say, well, I have no spatial resolution effects when this is of order 1. So kx times the Y length is of order 1. So you'd say, okay, I have an attenuation here. But for these other Reynolds numbers, remember this is in the logarithmic layer. We're not now down, we're at Z plus of 100 here, okay? We're considerably away from the wall. But you see, even in this region here, you get this dramatic attenuation of the energy, where conventional thinking would say, well, I only have a problem for wavelengths over here. But you can see I'm having them all the way down to here. So that surprised us a little bit. The other issue, which really, it is a can of worms. And the other issue, which isn't really well understood, is the effect of length to diameter ratio. And Hassan will talk a little bit about our the ISET initiatives and different. And it's raised interesting questions because different groups have different approaches, and the wire geometry, how you attach it, these sort of things. Obviously, there is actually a heat wave due to conduction, and now the effect of that is basically to reduce your frequency response. This is the classic correlation presented by Legrani and Bradshaw. So they document, they systematically vary out. So these are the small, so these I would say are fully resolved when you're getting down below 10. This is the number I would trust. But at this low Reynolds number, you can see that, depending on the accuracy of the measurement, is that 200 is the rule of thumb that we use. Can it be higher? It's not quite clear. These are our own measurements where we match L plus, but we vary L on D. And you have to do that by using different lines. It's a very tedious task.
Quick question on this. So this is primarily the Reynolds number difference between the two levels?
That's what we guess. This is just an arbitrary curve. This is an exponential function I just put on there for a trend. There's no basis for that curve. But in theory, if you analyze it, essentially the higher you go in Reynolds number, the less of a problem L is. But when and how, that's the issue. So we know the trend, but we're not talking. This is quite a high Reynolds number range, but we're seeing differences even over small changes, 1 to 5,000 in other studies. So this is something that concerns, and of course that's a problem because then you're limited in your LMD. That limits the length of your line for that geometry now. So that may mean we have to go to different designs. So this is again is the example. This is an extreme LMD, of course, but you can see the effect. It's very dramatic. Going to 100 also you get significant attenuation, but it's really across the entire boundary layer. The way to tackle that, you can go big, as we have with large facilities, pretty costly way to do things. Or as Lex Litz at Princeton is doing, is developing very small probes. Obviously in the superpipe, this is a first order problem, and this shows you these are conventional hot wire for a 5 micron, and this is the same scale. And using a MEMS technology fabrication, they're going down right now to 60 microns and below. So this is a photograph of one of their early wires, and some more photographs. The interesting thing is that if you make these out of single crystals, they're actually incredibly strong, and the smaller they are, more robust. So there is promise for this. And also what they're doing is, you can see here's a piece of a sensing element, and they're actually milling it with an ion milling technique to get even further down. So I think there's some exciting developments, but it's one of those things. So while we're waiting, conventional hot wires took a very long time, and I don't know if we've yet emerged. So while we wait, we've been looking at, could we model the unresolved energy in a sensible way? So what is that unresolved energy? What does it depend on? The naive approach is to assume something like a Wingard correction, where you say, well, I cut off at this wave number, and then I use an isotropic relation to fill in the existing energy. That's not going to work in a boundary layer. You're very far. This is the exact part of the flow where things are most anisotropic, and you really have to have a handle on physics in order to guide you. So, we ask ourselves the questions: what does it depend on? L plus, we know, is an first order effect. Equivalently, you can use L on eta, where eta is the Kolmogorov scale. In fact, this is the correct one to use. I say that because if you look at how the Kolmogorov scale varies across the boundary layer, essentially it's constant in this region. So it doesn't matter whether you use L plus or L on eta. But in the there's enough evidence, I think, to suggest that the smaller scales of motion scale with eta and the filamentary eddies that you see, any flow visualization that you do, things always come at about 10 eta. Okay, so that means and eta increases away, so that's actually helping us. So you choosing a fixed L plus is a conservative approach, and but L on eta is likely the correct way. But in this region, you can just interchange them as a constant factor. So what other issues? So this is just a cartoon showing a range of horseshoe eddies with a geometric progression of scales as argued by Townsend in the attached eddy hypothesis. And if you think about, so this is those smallest little eddies there. So basically the essence of the attached eddy, which gives a model which gives you a logarithmic dependence, argues that as you double the scale, you halve the population density, and you have a geometric progression. That gives you a universal constant. Of course, that can vary. But if you just use this to think about it, if the smallest eddy is going to be limited by a viscous process, and things will suggest that they've scaled with fine scaling, so about 100 viscous wall units. So that gives you a good handle on what range of scale you have, and you can think about what the attenuations are. Then obviously, so then you can think about how things contribute as you move away from the wall. And you end up convincing yourself that Ln Z is actually a parameter that needs to be taken into account. So if we use just, again, this is very rudimentary, but using this and this, can we come up with some sort of correction scheme? So we go back to this plot. As I said, this is for Ln D is not an issue in any of these data. But there is actually a trend in this. If you actually look at it in terms of a function of L plus and Reynolds number, you do see that things follow this surface. And on the basis of that, you can come up. Now, this is completely ad hoc. It's just a simple correction at that one point. And it seems to work really well. Why? Well, it doesn't really. Can we come up with other ones? Certainly can. But, you know, in fact, this doesn't make, this is L and delta, actually. That doesn't make sense in an extreme range, but over this data set it seems to work quite well. So just as for guidance, we can use this model that we presented Hutchins et al. So it's a simple algebraic relation. So we can say that if the missing energy is this at that point, well, then we can use it to guide our thinking. We know as we approach the wall that shortage of energy has to scale with Z plus. And by the arguments I just present, we're going to propose, this is just that things then will approach an Ln Z. So if you do that, well, you can just recast the problem. So I'm just basically using a function like that. It's at 15, it's 1, and then this forces you to switch over to Ln Z. This forces you to switch over to a linear distribution of the wall. And then you can correct data. And now you can correct it to any L plus that you want. So these are data at RE tau 7300. These are for 4 different lengths of hot wire. I'm going to match them back to this one at 22, and you see it works reasonably well. You know, if you wanted a rough and dirty correction scheme, you could use this. And so we tried that at a different Reynolds number, and it works okay. And we even went down to a low Reynolds number. These are Javier's data for turbulent channel flow at 934, and we mimic filtering just by using a simple filter, a Gaussian filter across the grid, and you get this sort of effect. And then if we correct it, again you get this sort of, so it seems to work reasonably well. But, you know, it is quite ad hoc. Now, can we go beyond the second order statistics? I say that because I think being able to just fit the turbulence intensities for the stringwise component, you can get that, but it can lull you into a false sense of security in that you feel like you completely understand the processes. Any correction scheme or the physics that you've used to guide it has to be consistent across a very large range and for other components. So one of the things that we haven't taken into account of all these very large, what we've seen in recent years, these very large scale motions or superstructures that we call them in boundary layers. We're sort of coming to the point where originally we thought these are the same, but we use this now for boundary layers and this for channels and pipes. I won't go into why. But these, that concept came about from rate hot wire experiments. Previously we had seen very large signals associated with spectra. That's what Kim and Avery did. But here, looking at instantaneous fields, by POV studies we had a very limited field of view. But by using Taylor's hypothesis, you get these very long, elongated, organized, streaky motions. they're not the near wall streaks, these are large scale that we've been discussing in the past couple of days. And to my amazement, Nick said, well, why don't we try it out in the desert in Utah? Originally we thought this was a problem with the screens in the tunnel. Actually, we first saw this in our tunnel in Minnesota, and I was convinced it was a problem. Then we did it in another little wind tunnel, we saw the same thing. Then we came down to Melbourne and did the same. Those are in Melbourne. And then we went out to Utah, and just by guiding, we chose the spacing. It took us 2 goes. But on the second, what we thought the spacing should be to match our, and again, we saw the same things under a neutrally buoyant case. These are not convective boundary layers. These are near neutral. This is the span wide, this is the array, this is 30 metres. In fact, because we have this vertical slice, you see that these things, again, are incredibly long, and they're also significantly high in the wall normal direction. So these are very large organised motions. And they carry a lot of the kinetic energy, so that's why and Reynolds shear stress, that's why we call them superstructures. And really the signature shows up in this outer peak, this sort of characteristic decomposition in the spectrogram with this inner peak associated with the near wall streaks and the peak in the intensity, and this large outer peak is associated with these motions, and that's normally in the logarithmic region. So again, the same plot. The only thing I want to point out here is this large-scale energy comes all the way down to the wall. And we saw that actually in our decomposition. When we decomposed the energy, we saw there was a significant contribution all the way down to the wall, and they're not affected by spatial resolution. Just a note of caution that if you go to very low Reynolds numbers, you may not see them. They only sort of kick in above about 4,000 where they're obvious, but they're there. Even below, in the DNS, they're definitely there, but it's a signal-to-noise issue.
These are multiplying spectra, right?
Yeah, that's right. And also an interesting observation, I'll try to wrap up quickly, is the fact that these things not only superimpose their footprint at the wall, they also modulate the process. So to show you that, so if you put a hot wire at this location, so here's a typical signature, and at the same time I have another wire simultaneously sampling. Now I'm looking at the large-scale signature, so if I filter those two signals and cross-correlate them, this is the filtered signals. If I cross-correlate them, I get a correlation coefficient of 0.7. As far as I'm concerned, that's 1. In the turbulent flow. This is above, there's no account for any spanwise meandering. You have to account, there's a nominal structure angle of about 14 degrees. This is just another realization here. So this is a wire at 15. This is from a wire deep in the log layer. And you can see the low frequency correlation is actually quite amazing. And this is not, I didn't have to try hard to find this. This is very present in the data. And that signal gets stronger and stronger as you increase your Reynolds number. It's also present in the DNS data. Well, the point about modulation, if you stare long enough at those other signals, this is a particularly good case. So again, this is the low frequency signal, which I said is associated with those big structures. If I concentrate on the low speed region, then you see this attenuation of the turbulence in all the components, and vice versa. Yeah, so these superstructures are not just the low speeds, the associated high speed, they go hand in hand. So while you have the high speed, you get this amplification. So this is what we mean by this amplitude modulation. And this is sort of a cartoon representing that process. So you have these very large, I'm not talking about necessarily this is sort of in the mean sense, or on a particular long time scale, you have these type of patterns. And in a cross section, so what you find is that below the low speed regions, you have these associated roll modes. Now that doesn't mean that these things are short, they're not at all. But on average, if you're conditioning average, that's what you get. And the net effect is that you have this attenuation of turbulence below. There's a change where actually you get attenuation above. This is sort of related to this sort of packet motion, or it's just simply related to the fact that you have shear layers and therefore there's an there's increased water productivity on these interfaces, which makes a lot of sense. The high speed, you get this increase in attenuation, and it acts as a direct modulation. So we could, so this is something I presented a year or so ago at Cambridge, and as very preliminary. We've been working on this further, and we're quite happy with it now. That can we actually use this to predict what happens near the wall? In fact, it's so hard to access that. Could we stop in the log region and then predict everything below there? That's the goal. And so this is the formula that we're going to use to do that. What it is, just made up, it's very simple. There's a superposition of the large-scale signal. So U2S is a wire at location 2, which is in the log layer, and it's the large scale. I don't even need the full signal. This is what you get in an LES. Okay, it's a large-scale signal in the log layer. That's my own. Now there's a correlation coefficient, which I know, I can measure that, and then I'm going to assume it's universal. So that superimposes a signal. This is essentially what the attached eddy hypothesis would argue. But different to the attached eddy, there's an additional amplitude modulation that you have to take into account. Now, if you're looking only at second-order statistics, this will not matter, because you won't see this. This is in the phase information. If you're looking at third-order statistics or others, this is very important. Okay, so that's a slightly, and it is non-linear. This is linear, this is non-linear. And so here, this is just a modulation. So the way we get this is we do a series of experiments. I use simultaneous measurements at 2 locations, one always in the log layer, and then I'm going to traverse this, and then, so I know that, I can solve for this. Now this thing is we call the universal signal. This is what, if the law of the wall or wall scaling worked, which it doesn't, but if it did, this would be the characteristic representative statistical signal that you would get. And we call this the universal signal. It's one where there's no superimposition from the large scales, it's a complete decoupling of inner and outer, and there is no such thing as modulation. So we solve for this, then we say these are fixed forever, and you characterize them as functions of t plus. And so we've done this systematically at different positions throughout, and then you've got them, and there they are. You know the correlation coefficients. Now you can go back, and I know this. All I need is this. So I need one signature in the log layer, and now I can predict everything below there. That's the roadmap of what we do. But here's some results. I'm running out of time. So these are measurements. This is pre-multiplied spectra at Z plus 15 over a range of Reynolds numbers. This is the prediction. And this is a real prediction because I don't even have a measurement for that one. That's in Utah. Because I have lots of measurements in the log layer, nothing near the wall. Everything does that. But you see actually what you predict. This predicts this sort of bimodal distribution. This is why I think the peak actually may change. But also I should, these data, these U stars were done with an L plus 22 wire. So they are attenuated a little bit. Okay, so actually we should go back and do a little smaller wire still. But that's, that can be. And in fact, when you get U star, you only have to do it for one Reynolds number. So that's quite good. So that was at this, so this is the spectra again. So this is so we've done it at a lot of points. So again, this is my measurement location. So one wire. The blue is everything we reconstructed the model. And these are measurements, and you can see it works really well over lots of, this is the prediction for the Utah result, which you can take with a deep grain of salt. But you definitely, so now you have a model, and of course now I can correct the spatial resolution with that too. But this, I feel, has much more physics in it. And you can, of course, we have to test it for other quantities, but at least it's capturing these processes. So that's just the stresses they have to work as the spectra does. So again, measurement here, blue is prediction, but then also what's interesting now, we can look at the skewness, and we predict actually that the change in the sign of the skewness near the wall as an increase in Reynolds number. This has always sort of been a mystery, why does that happen? This shows you that it's part of this modulation process. And you can go to anything you want, even either order -6 moments. A lot of error in those, but the trends are consistent. So I'll stop there.
Thank you very much. We have time for one or two short short-term comment.
I would like to make two naive questions if time permit. The first one concerning the outer peak in the spectrum. That means that they are at large scale. So can we trust Taylor algorithm converting time series into spatial information? Secondly, the secondary peak it emerges very cleanly, I mean at least within the experimental problem that we were mentioning, when you analyze the pre-multiplied spectrum. Of course, we were associating that to large-scale motion, so the signal should be also in spatial kind of statistics. I mean, without taking Fourier transform and pre-multiplying, you find it in second-order correlation and error.
Absolutely.
So I would like to know if there is some evidence that you can extract that scales also for statistics, not Fourier transform.
So your first question, does Taylor's hypothesis play a role? Absolutely, if you're looking across the position of that outer peak down towards the wall, it's a first order effect. Does it change? So what we've done is we've varied a whole range of convection velocities, and yes, you get distortion, but not in that outer region. So you don't. There's no way that disappears. That's not an artifact of convection. But we don't. We need to have a true spatial measurement. For other statistics, I'm not aware. You can infer, say, from the stresses, what that relation would be. But I'm not aware of any others. But you're absolutely right. You have to see many other things. It's most obvious when you look at the spectrogram like that. How to see it in other quantities. The problem with statistics is always some integration across those scales. And so, you know. But, yeah.
We are trying naively to do something with second-order structure function, so to normalize them like.
Sure, and that's directly related to the spectrum.
You end up with a scale, but which is by one order of magnitude different. So it's not clear to me where the physics is in this secondary peak. I mean, it is clear that it is clear, but
so typically you get peaks around 6 delta in boundary layers. And you're saying you get 0.6?
No, something. Yeah. So I mean, because I was wondering, you should find this in
But you're talking about DNS?
Yeah. I mean, yes. We are using the data that Javier Jimenez was published in the website.
So. You won't see it at the low Reynolds number simply because the signal is too weak.
Yeah, but still in the spectra you see that you have this kind of.
Yeah, but you don't. I don't think you have the scale separation to show it. So it becomes very difficult partitioning what's large, what's small. But absolutely, you have to look at other quantities.
Okay, I think we need to stop there before we pick up